Alright, so today in Unit 7 we'll be talking about exploring exponential models, just talking about everything that just works with it. So first off, let's start drawing. Okay, now we're mainly going to stay in the first quadrant because that's where a lot of exponential models happen. Okay. Alright, first off, exponential models, they will pretty much always cross at y equals 1. Some of you guys are probably wondering, well, let's take a look at the actual equation. Y equals a times b raised to the x power. Okay, well, if x is 0, guess what? This turns into 1. Okay, so that's why the y-intercept's pretty much always going to be 1. Okay, now asymptote, we've already talked about this quite a bit before, you guys. But basically an asymptote is a line that the function actually approaches but never touches. Okay, and that line is usually y equals 0, because no matter what, you're not going to go below that. You're not going to actually get 0. There's no x that you plug in that will get you a number that's going to be 0 if this number's not 0 and this number's not 0. Okay, so there's no x that will exist on that. Okay, now decay factors. If it is decaying, that means b is between 0 and 1. Okay, so it's decreasing. Okay, the actual exponential decay comes because of that. Okay, so you're exponentially decaying. So in other words, this graph will go from going up and to the right, it will actually go down and to the right. Okay, so that's exponential decay. There we go. Okay, now the actual exponential function is this, so that's pretty simple. Exponential growth would be this red one right here. Okay, and the growth factor would be the b, so the decay factor would be b somewhere between 0 and 1. Okay, and the growth factor would be b being greater than or equal to 1. Okay, so that's as simple as that. Alright, now that's probably leaving a lot of you guys with, oh, what's a? Well, a is actually the initial amount. Okay, so as long as you know the initial amount, the growth or decay factor, and then t is usually measured in number of years, you should be good to go on exploring exponential models. Alright, so here's everything that you can do with it. Now a is definitely going to increase and decrease the actual y-intercept as well. So instead of a is basically the constant in front being multiplied. So if this turns into 1, then whatever a is controls where the y-intercept is. So if I make it 1.4, guess what? 1.4 is the y-intercept. If I make it 3.8, 3.8. If I make it negative 3.1, it's going to be there. So you have to imagine that while we're working on this stuff, okay? Alright. Now, the reason why I made b 2 and start out as 2 is because if I make it 1, it's going to be just a straight line. So b is 2. If I make b larger, notice how that it always stays the y-intercept at 1. And no matter where I go, well, if I go negative, this is going to be an issue because I can't graph that. Okay, so you can't go 0 or negative. Plus, there's nothing to graph there when it happens like that. Okay, so we leave this at 2. Alright, now if I move h at all, okay, what it's actually going to do is it's going to increase the power. So instead of being just 1 right here at 0, okay, if I make it a 1, it's going to be bringing it to the power of 2, and it's just going to be working its way up and just messing around with everything. So, for example, if I zoom out, okay, 2 would be 8, and then 1 would be 4. You know, I mean, it's increasing the exponent by 1. Okay, let's move it back. Alright, now k is going to control the movement up or down. It actually controls the asymptote, the vertical shift. So whatever k is, you're probably going to be dealing with that as the asymptote. So whatever the number is being added at the end, that's going to be your asymptote for the exponential functions. Okay, so what we're taking a look at is, like, let's say you actually had a problem to deal with. Okay, let's say that your actual equation was when I'm going to have $120 in a bank account if I start out with $50, okay, and I have a growth rate of 5%, so that's 0.05. Okay, well, it's actually going to be 1 plus. Keep always forgetting that. Okay, and we're going to raise that to the x power. Okay. All right, so we can actually find out that timeline of when we're going to get 120 by graphing both. So we go y equals 50 times 1.05 raised to the x power. Okay. All right, now this is going to be really big because we're starting out at 50. If you remember, our a is at 50. Okay. All right. And let's say that this was gaining interest yearly, that type of thing. Okay. So what I would also do is graph 120 at the same time, just to see where they cross. And I can actually tell you that after 17.9 years, that bank account will turn into $120 with that bank account with 5% interest. That's a heck of a long time just to work with this stuff. So when you are working with this, you might be dealing with a different compounding of interest. So let's say that instead of just being compounded every year, you are actually compounding every month. Let's say 12. So what you would do is you would divide the percentage by 12. 1 plus, yep, that's right. And then you would times that percentage also up here. So that would be times by 12. Okay, so we put the 12x here. All right, we change this. 0.05 divided by 12. Okay, so we actually have this right here. All right, and you would see that it would be 17.95 years. So 17 and a half years. So it'd shave off a couple months off of your thing. All right, and the more time you compound interest, you just work across it, you should be able to find it. But basically, the whole point of this stuff is to just go, okay, here's where I'm starting out with, here's where I end with. I graph both equations, both lines, see where they cross, and that will actually give me a pretty darn good answer of what to expect, okay? All right, that is it for working with exponential models. Good luck, you guys, and I hope you have a great day.